Okay, can everyone see the screen? Can everyone of you see the screen?
Yes, sir.
Okay. So, in the last class, we have discussed about the molality, mole fraction. We had learned about them. So, in today's class, I told you we'll be learning about another new term, another new unit of concentration, and that is known as the parts per billion. Parts per billion. So, what is this? This is also not that used in our class 11, 12 level, but you should know about them because if because it is not that much use. If question comes from here, it is mainly very easy questions. So parts per million, it is the number of parts of a component present in present in present in per billion part of the solution. So what does this mean? Suppose you have 0.002 gram chlorine in 500 ml water. So suppose 0.002 gram chlorine is present in 500 ml of water. So then what are you getting? You are getting to see that concentration is 0. Weight of the solute, weight of solute 0.002 divided by volume of the solution, that is 500. So 0.002 divided by 500. So that is coming out to be equal to 4 into 10 to the power of minus 6. So if you do this calculation, you will get it to be as 4 into 10 to the power of minus 6. So this is the calculation. Now what is the problem over here? Problem is this value is very small. It is basically 0.000004. It's a very small value. And it is very quite difficult to work with such a small value, and that has so many points. We all like to work with simple numbers, whole numbers. We like to do calculation with whole numbers. Suppose if you get 3.569 into 10 to the power of minus 6, that is very difficult to work. Every one of us want to work with a number which can be easily expressed. So that is why what we do is we multiply this because it is so much small. We multiply this with 1 billion, that is 10 to the power of 6. 1 million is equal to 10 to the power of 6. 1 million means 10 to the power 6. 1 billion is 10 to the power of 9. While 1 trillion, that is 10 to the power of 12. So here we are actually increasing the concentration. We are multiplying it with 10 to the power of 6. So what do we get now? Then we are getting 4 ppm. That is parts per million. 4 parts per million. Now as you can see, now this data is easily expressible. This is a good data. 4 ppm. 4. So we can easily express it, and also we can easily do calculations. So parts per million is, so that's when the concentration of the solution is very low. When the concentration of the solution is seen to be like very, very low, then we increase the value of the concentration by a million times. So we are multiplying it with 10 to the power of 6. This makes the value a bit larger and easy to express and easy to calculate. Now, why do we actually multiply it? Because this parts per million is the generally preferred unit for all these atmospheric pollutants. If you follow the newspapers, then you know that Delhi has your pollution problem in the winters. Okay, there's a huge pollution every year in New Delhi. So if you follow the newspaper over there, you can see that actually they express those units of different pollutants in the air in this picometer, sorry, in parts per million. Because with respect to the air, which has a huge amount of volume, the amount of pollutants present, that is a much smaller value. So they express them in picometer. If you follow those newspaper, you can see that suppose SO2 is present in 36 picometer, 36 parts per million. Nitrous oxide is present in the air in 70 parts per million. Like this way, it will be expressed in the newspapers. So that is why when you are explaining something in the newspaper, it has to be easy. You cannot use so many decimal numbers. That is why the preferred unit to express the concentration of pollutants in the air, that is basically parts per million. Or if you see any news articles where suppose there has been some kind of accident with the pollutants present in water, that may be lead or any other metal that is present, so that news reporting is also done where the concentration is expressed in parts per million. So parts per million makes the data look easy. It is similar to, suppose if you have to measure the distance between two galaxies. Okay? If you have to measure the distance between two galaxies, then obviously our preferred unit is light year. Because if we say that the distance between two galaxies is suppose 2.5 light year, that is much easier to express compared to saying that the distance between two galaxies is 13.694 into 10 to the power of 26 kilometer. So that is very difficult to say in this way, and difficult to remember also, difficult to understand such a big value, and difficult to do further calculations. So that is why we have introduced a new unit which is light year. And light year, if we use, because it's a much bigger unit, then we can actually make the value much smaller. Which, for example, we can say it in this way: 2.5, 3.5, like this. So telling 3.5 is much simple. Doing calculation with it is much easier to understand. So that is why instead of kilometer, for much larger distance, we are using light year unit. Just like that, similarly here also, if the concentration is very small, as is the case in our example, what we are doing, we are increasing the value. We are magnifying this value a million times. That is, we are multiplying this with 10 to the power of 6. And that is why it is called parts per million. Okay, is it clear to everyone? So let us see the formula for this parts per million. That is, ppm of a compound that is equal to mass of the component divided by total mass of solution. Into 10 to the power of 6. So as you can see, we are magnifying this with a million times. So just like you have parts per million, you also have, suppose now the concentration is even less, even much lesser than parts per million as well. That is why we have parts per billion, ppb. ppb is also the preferred unit for measuring this atmospheric pollutants in air. That is equal to mass of the component, same formula, just here we multiply with 10 to the power of 9. Total mass of solution into 10 to the power of 9. So these are the formulas for calculating ppm and ppb. From the examination point of view, I told you this is not that common for parts per million and billion questions to be asked. Okay, I'm saying not that common. I'm never saying that it will not come. And because it is not that common, so if question comes from here, it is mainly easy question. Just simple formula, you put the formula, you put the data in the formula, you get the sum. So yes, this is your parts per million and parts per billion. So is it clear to everyone? The basic idea behind this thing? Is it completely clear to everyone? Of why you are using the unit parts per million? Hello, can you hear me, everyone?
Yes, sir.
Okay. How many are there in the class at this moment?
5.
Okay. So now, as I told you, we have done with the concentration factors. So, Acha, tell me, is parts per million dependent on temperature or independent of temperature? Is parts per million dependent or independent of temperature? Is parts per million dependent or independent of temperature? See, can you see anything related to volume in the equation? There is no such thing related to volume. That means it is independent of temperature. Okay, had there been presence of volume, then we could have said that it was dependent. This is independent of temperature. Now, so now we have the next one, that is the mole concept. Acha, in your school they are teaching the second chapter, atomic structure, or have they completed atomic structure also?
No, now structure of atom is main.
Okay, structure of atom is being taught.
Yes.
Did they just start or did they? Are they almost at the end of that chapter?
No, from first only.
Achha, they're just starting the chapter.
Yes.
So follow your school classes also, because the older students have already seen it. So yes, you can easily understand it. You can do well in your class as well. So you have the mole concept thing. So for mole concept, I will follow the same table which was done before also, because that gives us a very nice idea. So what is this mole? What is a mole? Mole is basically just like we say 1 dozen is equal to 12 substances. Okay. Just like in mathematics, we have done dozen. 1 dozen is equal to 12, 12 amount of anything. So a dozen is a collection of substances. 12 things together is called a dozen. So here also, mole is a collection of particles. Okay. A mole is a collection of particles. A mole is a collection of particles. How many particles is it? It is Avogadro number of particles. That is 6.023 into 10 to the power of 23. Okay. And this is only known as the Avogadro number, denoted by the symbol Na, or sometimes it is also denoted by N0. So when we have this many particles, which is like huge number of particles, as you can see, 10 to the power of 23. So there are 23 zeros like this. So this many particles together is known as a mole. So a mole is a collection of particles. And how many particles is it? 6.023 into 10 to the power of 23. So this many particles, when they are coming together, then it is called the mole. Okay. So a mole is a collection of Avogadro number of particles. And Avogadro number is 6.023 into 10 to the power of 23. Okay. And you have to remember this value. This is a constant Avogadro number. This value though you have to remember. Nothing can be done regarding it. This value you have to remember. So then, now what is the Avogadro's law? So let us see the Avogadro's law. It says under the same condition of temperature and pressure, under the same condition of temperature and pressure, under the same condition of temperature and pressure, equal volumes of all gases equal volumes of all gases contain the same number of molecules. So under the same condition of temperature and pressure, equal volumes of all gases contain the same number of molecules. And this is known as the Avogadro's law. So this does not matter which gas you are taking. If you take at a particular temperature and pressure, whatever you gas you take, be it hydrogen, oxygen, carbon dioxide, sulfur dioxide, whatever gas you take at a particular condition of temperature and pressure, equal volumes of all these gases have the exact same number of molecules. So this is what our Avogadro's law is saying. Okay, the equal volumes of all gases have the same number of molecules. Okay, so now let us understand the significance of this law with different examples. Okay, and for this I will be doing a table very similar, exactly similar to the one that we had done before. That is, suppose we write it in this way: 1 mole of. Achha, by the way, do you have any exam nearby, like school test or anything like that? Tell me beforehand, okay? Did your school tell when you are going to have your first class test or unit test, whatever?
Yes, from 22.
From 22. Okay, and what will be the
Yes.
chapter? This chapter only then.
Sir, don't know.
Achha. Okay, I think that will be this chapter only. Okay. So suppose we start with carbon dioxide. Carbon dioxide. CO2. So tell me what is the molecular weight of carbon dioxide? Quickly calculate and tell me what is the molecular weight of carbon dioxide? What is the molecular weight of carbon dioxide? What is the molecular weight of carbon dioxide? It is basically 24 plus 2 into 16. You have to remember um, this atomic weights. You have to remember all this atomic weight. 12, sorry. So that is equal to 44. So carbon dioxide's molecular weight is coming out to be 44. Now, how much volume does it occupy? I told that equal volumes of all gases contain the same number of molecules. So the volume occupied by one molecular weight of a substance, any gas, is 22.4 liters always. Okay, at normal standard temperature and pressure. STP mane standard temperature and pressure. So STP means standard temperature and pressure. Standard temperature and pressure. Standard temperature and pressure. So the volume occupied in this case is 22.4 liters. 22.4 liters. Okay. Sometimes you do not want to express it in liter unit, you want to express in some other units. So suppose if you want to express it in 22.4, it will be decimeter cube. 22.4 decimeter cube. So that is another unit. Or if you want to express it in cc, that is cubic centimeter. 22.4 cubic. If you want to express it in cubic centimeter, then it will be 22400 cc. That is cubic centimeter. Cc is basically cubic centimeter. Cubic centimeter, which is given by centimeter cube. So this is the cubic centimeter. Okay. So one molecular weight of a substance has a volume of 22.4 liter. Whatever gas you are taking at standard temperature and pressure, it is going to have the same volume. Okay. And in one molecular weight, how many molecules will be there? There are Avogadro number of molecules. So it has Avogadro number of molecules. 6.023 into 10 to the power of 23. Okay. So that means 44 grams. That is one molecular weight of carbon dioxide has 6.023 into 10 to the power of 23 molecules of carbon dioxide. And it has a volume of 22.4 liters. Okay. Now see, if I use oxygen also, oxygen. Now what is the molecular weight of oxygen? The molecular weight of oxygen is 32. So 32 is the molecular weight of oxygen. Now under this oxygen also, 32 grams of oxygen has a volume of 22.4 liters, and the number of molecules present in 22.4 liters, that is Avogadro number. Why is the number of molecules same? Because Avogadro number says that equal volumes of all gases contain the same number of molecules. Equal volume of all gases contain the same number of molecules. So as you can see, 22.4 liter of carbon dioxide has Avogadro number molecule, and according to the law only, equal volume means 22.4 liter of oxygen, this also has Avogadro number of molecules. So that's it. Equal volumes of all gases has the exact same number of molecules. If I take ammonia, NH3, that is also a gas. So what is the molecular weight of ammonia? It is 70. 70. Now this also, one molecular weight of the substance has a volume of 22.4 liter, and equal volume has the same number of molecules, that is Avogadro number of molecules. So thus in 17 grams of ammonia, you are going to have Avogadro number of molecules. So whatever gas you take, that doesn't matter. If you are taking the same number of volume at a particular temperature and pressure, then it has the same number of molecules. Okay, is it clear to everyone? Is this clear to everyone? If you take hydrogen also, what is the molecular weight of hydrogen? It is 2 gram. 2. Now 2 gram of hydrogen has a volume of 22.4 liter. Okay, so one molecular weight of a substance, that is known as 22.4 liter. Okay, and how much number of molecules are there? Avogadro number. Okay, is this clear to everyone? So one molecular weight has 22.4 liters, and the number of molecules in it is Avogadro number. Is it clear to everyone till this much?
Yes, sir.
Okay, what about the others?
Yes, sir.
Okay, then now let us see this one, number of atoms segment. Achha. Now tell me, in one molecule of carbon dioxide, this is one molecule, right? CO2, one molecule. How many carbon can you see? How many carbon can you see in one molecule? There are only only one carbon is present. How many oxygen can you see? You can see two oxygen. So one molecule of carbon dioxide has one carbon and two oxygen. So now you tell me, this many molecules of carbon dioxide are there. One molecule has one carbon. Avogadro number of molecules will have Avogadro number of carbon. Simple thing. So how many atoms are there? The carbon atom is Avogadro number. that is 6.023 into 10 to the power of 23 atoms of carbon is there, because one molecule you can see one carbon. Does it Avogadro molecules? Avogadro carbon. Then the next one, O2. That is one molecule, you have two oxygen. In one molecule, you have two oxygen. Thus, in Avogadro molecule, you have 2 into Avogadro number. One molecule, two oxygen. In one molecule, you have two oxygen. In Avogadro molecule, you have 2 into Avogadro number, just like basic unitary method. So the oxygen atoms are 2 into Avogadro number. So this many oxygen atoms are there. Okay. Then see the next example. In one oxygen, this is one molecule of oxygen. How many oxygen atoms can you see? Two oxygen atoms are there. Two oxygen atoms are there. So in one molecule, two oxygen atoms are there. In one molecule, two oxygen atoms can be seen. In Avogadro molecule, Avogadro number of oxygen atoms are there, 2 into Avogadro number. So how many oxygen atoms are over here? In one molecule, you are getting to see two oxygen. In Avogadro molecule, it will be 2 into Avogadro number. So that is 2 into Avogadro number. Avogadro number, as you know, is denoted by the symbol of Na. So we are writing it as Na only. Then see the next example, that is ammonia. So this is one molecule of ammonia. How many nitrogen atom is there in one molecule? One. So now you tell me how many hydrogen atoms are there? 3 hydrogen you can count. So now you tell me how many nitrogen atom will be there in total. How many nitrogen and how many hydrogen? Tell first.
Three hydrogen.
How many?
One nitrogen and three hydrogen.
Yes, that is okay, correct. Now I am asking you how many nitrogen and hydrogen is present in Avogadro molecules of ammonia. That is 6.023 into 10 to the power of 23. In this many molecules, how many nitrogen and hydrogen is present?
One into Avogadro number in nitrogen.
Yes, it is 1 into Avogadro number, because as you can see, in one molecule, one nitrogen is present. In Avogadro number of molecules, 1 into Avogadro number. So you can simply write Na number of molecules. Then how many hydrogens are present?
3 into Avogadro number.
3 into Avogadro number, because one molecule has 3 hydrogen. Thus Avogadro molecule has 3 into Avogadro hydrogens. So yeah. So is it clear to everyone? Are you getting it? So now you tell me hydrogen. How many hydrogens are there in one molecule? How many hydrogen are there in one molecule? 2 hydrogen. So what is the total number of hydrogen atom? What
2
is
into
that?
Avogadro number.
Yes, it is 2 into Avogadro number, because one molecule has 2 hydrogen. Avogadro number of molecules is going to have 2 into Avogadro number. Is it clear to everyone? Is it clear? Please let me know. Okay, then see, we can take even more examples. Suppose H2SO4. The molecular weight of sulfuric acid is 98. This, if you do it, you will see that it will always come 98. Answer. Now, sulfuric acid is not a gas, so we are not considering the volume. Okay. But 98 grams of sulfuric acid has Avogadro number of molecules. So one molecular weight of any substance, whatever substance you are going to take, one molecular weight always contains the Avogadro number of molecule. So now you tell me how many hydrogen atoms are there in total in Avogadro molecule in H2SO4. How many hydrogen, how many sulfur atom, and how many oxygen atom? First, tell.
The 2 into Avogadro number.
2 into
Hydrogen.
Avogadro, okay. Then,
1 into Avogadro number.
and how many oxygen?
4
4 into
Avogadro number.
Avogadro number. Because as you can see in one molecule, you are getting to see 2 hydrogen, 1 sulfur, 4 oxygen. And then you simply find it for Avogadro number of molecules. Okay. Then suppose if you take magnesium chloride, MgCl. Magnesium chloride. Okay. So magnesium is 24. Chlorine is 35.5 into 2, that is 71. So it is coming at 5 and 9. So magnesium chloride's atomic weight is, molecular weight is 95. And you are getting this to be as, so 95 grams of magnesium chloride has Avogadro number of molecules. Now you tell me magnesium chloride, you have done this in class 10. Is it an ionic compound or is it a covalent compound? Is magnesium chloride an ionic compound or a covalent compound? It is ionic compound, Mg2 plus Cl minus 2Cl minus. So it is ionic compound. So here you have to write it as with respect to the number of Mg2 plus ion. You cannot write anions, those atoms over here, magnesium atom, calcium atom. Then it will be wrong. You have to think it with respect to the number of ions. So how many Mg2 plus ion is present? That is Avogadro number. And how many Cl minus ion?
2 into Avogadro number.
2 into Avogadro number. So here you have to think with respect to the number of ions. Okay. Then let us see the next column of the table. That will be number of electrons. Number of electrons. Achha. So now you tell me how many electrons are present in carbon? How many electrons are present in one atom of carbon? Carbon has 6 electrons. Carbon has 6 electrons. Because the atomic number of carbon is 6. So a carbon is having 6 electrons. So one atom of carbon has 6 electrons. Avogadro number of atoms of carbon will have 6 into Avogadro number. So one carbon atom has 6 electrons. This you have to remember from the periodic table, 6 electrons. So therefore, total in Avogadro atoms, how many do you have? 6 into Avogadro number. 6 into Avogadro number. Then same for oxygen. See, how many electrons are present in oxygen? 8 electrons are there. 8 electrons are present in oxygen. So one atom has 8 electrons. Avogadro atom has 8 into 2 into Avogadro number. So that is 16 into Avogadro number. 16 into Avogadro number. Okay. So this is how you do it. So for this one, you need to know the atomic numbers. Then tell me here how many oxygen atoms are there. One atom has 8 electrons. So this many atoms will have 8 into 2 Avogadro number. That is 16 Avogadro number. Then tell how many nitrogen atoms are there. Total how many electrons of nitrogen is there. One nitrogen has 7 electrons. From periodic table, one nitrogen has 7 electrons. So this many nitrogen will have 7 into Avogadro number. How many hydrogen electrons are there? One hydrogen atom has 1 electron. Atomic number of hydrogen is 1 only. So 1 hydrogen, 1 electron. This many hydrogen will have 1 into Avogadro number. Then here how many do you have? 1 into this many electrons are present. Then here same also. How many sulfur atoms are there? The atomic number of sulfur is 16. Atomic number of sulfur is 16. So one atom of sulfur has 16 electrons. So Avogadro number of atoms will have 16 into Avogadro number of electrons. Then one oxygen has 8 electrons. So now 4 Avogadro number will have into 4 8. That is equal to 32 Avogadro number electrons. This many number of electrons are present. Then how many electrons are present in Mg2 plus?
12.
See, the atomic number of magnesium is 12. Atomic number of magnesium is 12. Here there is a shortage of 2 electrons. So how many electrons in total? 10 electrons. So 10 into Avogadro number. Then see for chlorine. Chlorine has an atomic number of 17. Here you have 1 electron extra. That is 18 electrons. So 18 into 2 into Avogadro number. So yeah. So this is how you do this table. And this is what the mole concept is. This is how you apply the mole concept. Using this mole concept, we can find out how many molecules, atoms or electrons or volume is present in a particular amount of a substance. So is it clear to everyone? Is this table clear to everyone? This table is
Yes.
just an example thing. Now you need to apply this in different numericals. But for understanding it is clear. Has everyone understood it? How we are finding out molecules, atom, electrons and everything else? Have you understood? I want reply from
Yes.
others. What about the others? Is it clear?
Yes, sir.
Okay. So yeah, that is the mole concept thing. So that's from here we can actually conclude that 1 gram molecular mass of a molecular compound, 1 gram molecular mass of a compound or molecule, whatever, that is equal to 1 mole. So molecular weight of anything, hydrogen, oxygen, glucose, whatever. If you take molecular weight of a particular substance, then that is the 1 mole. That is known as the 1 mole of that substance. So 1 gram molecular mass of any substance that you take, that is equal to 1 mole. Okay, then, and this 1 mole has Avogadro number of molecules. So 1 gram molecular mass of a compound, as we have seen from the table, this contains Avogadro number of molecules. And that only occupies a volume of 22.4 liters. So, whatever you take, one molecular mass of a substance has 1 mole, that is only known as the 1 mole of that particular thing, and it has Avogadro number of molecules, and it is occupying a volume of 22.4 liters. Okay, so this is just a kind of summary of the table only. So it is nothing new. We have already seen this thing in the table. Okay, so yes, so this is the thing about your mole concept. Now this is easy to understand, nothing as such critical regarding it. Now what we need to do is we need to apply them in numericals. So technically we have completed with the theory segment of this chapter. All the theories that we had, that has been done. So now over the next few classes, what we are going to do is the numericals. So maybe for the next week class that we have, we will be practicing the numericals from this particular chapter. Because theory we have done, and as I have told you multiple times, that in this chapter, numericals are the most important thing. So we'll be seeing certain different kinds of numericals that you can expect in your examination. So yes, but what I want you to do is that before the next class, what you should do is to remember all the formulas so that you can also actively participate in the question solving. It should not be like I am only solving the sum. Then it will be basically my practice, not your practice. It is me who I am practicing. So you should also remember the formulas so that whenever we are doing a sum, you can actually identify the formula. And thus, if you know the formula, then you yourself can also think out. Because as I have told before, the chemistry sums are not that difficult. Compared to chemistry, physics, and mathematics, numericals are much tougher. Chemistry numericals are not that tough. Most of the chemistry numericals are like if you know the formula, you put the values in the formula, you will get to see that there is one unknown quantity and you find it. So suppose in an equation, out of the 5 variables, 4 will be given to you. You have to find the unknown variable. So most of the chemistry sums are simply putting the values in the formula. It is not like physics or mathematics where you have to think much how to modify the formula and all those things. Those things are not there. Chemistry numericals are pretty straightforward. You know the formula, you put the values in the formula, and you get your answer. So that is why remembering the formulas in chemistry is very, very important. So before the next class, that's your homework. That is, I want all of you to remember each and every formulas and theories that we have done, so that whenever we are doing the numerical, you yourself can think how the approach of the sum is. Okay, am I clear to everyone? Am I clear?
Yes.
Okay, so then you have to do that, and I'll be stopping here today because we have completed the theory section. So yes, we prepare that, and then in the upcoming classes, we will be practicing the numericals. Okay, so then that's it. I'm disconnecting the call then. Bye everyone.